Now we'll discuss with more details, because you see why I'm spending extra time for this topic, because based on this icon only we have this chapter 5 classification of the air conditioning systems. That says an understanding this is important. So here with the line diagram we'll try to understand all these components. You see, this is a in actual practice you'll find flash chamber, accumulator, and some other devices. At this level, the four major components, just to understand the concept. Okay. When we deal with the classification of the air conditioning machine, you'll find more details. At this level, just focus on the concept. So the four major components, one is a compressor. Second, this heat exchanger is called condenser. And this heat exchanger is called evaporator. And here you'll find expansion device. It can be a throttling valve. It can be a capillary tube. You'll find the different types of expansion valve. Okay, so at this level, just focus on the concept. So the cycle starts from compressor, right? And if you consider this high and low side, you see the compressor and condenser comes under high side, and the expansion and evaporator comes under low side. Low side, high side means I'm talking about the pressure and temperature. Suppose if you draw the line, so you see the left side is a high side and the right side is a low side. Okay. So now with respect to the theory which I have given in the notes, let me mark the points first. You see here the points are given, but before this, quickly some more points I added. You see the vapor compression cycle is based on the principle that a refrigerant can change from a low pressure, low temperature vapor to a high pressure, high temperature vapor, changing its state through compression and expansion. We'll discuss how exactly. And remember, it's a closed system. So what is the difference between closed and open system online?
Closed means loop system.
Refrigerant will not flow.
Refrigerant will
You see,
flood in
technically, with respect to thermodynamics, closed system means only the heat can transfer the system, not the mass. In case of open system, the mass and heat both can cross the boundary of the system, but closed system, only the heat will transfer, the mass will not transfer the system. It means, you see, in this cycle, the refrigerant is running within the cycle now, it's not coming out from the system. Only the exchange of heat. So we can consider this as a closed system. And it's used as a refrigerant. And what is refrigerant we already discussed. So now you see point 1 to 2. Let me mark this point so that you'll get the clear idea. Point 1 to 2, leaving the evaporator. The refrigerant at the low pressure and low temperature and pressure, it uses again to achieve the refrigerant effect continuously. So point 1 to 2 here is related to, you see, 1 minute. Just let me mark this so that you'll not get the confusion. You see condition at point 2. Condition at point 2 means we require a high pressure and high temperature. So let me mark this first. Avoid confusion, or else without marking also we can learn, but the theory to avoid confusion which I've given in the theory, I'm going to mark. You see, I'm considering this point as 1 and this is as 2, and before expansion I'm marking this as 0.3. After expansion I'm considering this as 0.4, then again 4 to 1. You see, the cycle is 1 to 2, one process, 2 to 3 is a process, 3 to 4 also a process, and 4 to 1 also a process. Okay, so with respect to these points we'll discuss, and it's very easy. So you see, the cycle starts from the compressor, and remember, in compressor you'll find the refrigerant in what state, liquid or gas?
Gas.
So remember, refrigerant in compressor, refrigerant you'll find in the gas state only, because the compressors are designed to handle the refrigerant in the gas state. First point. And second point, what do you think? Liquid and gas, both are compressible or only gases are compressible? This one, if you compare, you see, if you compare liquid and gas, comparatively gases are more compressible, but it not mean that liquids are not compressible. Liquids are also compressible, but very less compared with the gases. So that's the reason in actual practice, just we are considering gases are compressible, liquids are not compressible, but liquid also slightly compressible, but under high pressure. So even liquid also compressible, but practically we are considering the gas are compressible. So inside the compressor, the refrigerant should be in the gas state, because we are considering gases are compressible. And when you switch on the compressor, how we can switch on the compressor? By supplying the electrical energy. For example, when you plug in or when you supply the electrical energy to the compressor starts. You may find the different types of compressor that we'll discuss later, like centrifugal, reciprocating, etc., that you'll find at the time of classification of machine. And at this level, you know what is that compressor. Compressor is used to compress the refrigerant gas state. So when the compressor compresses the refrigerant in gas state, what will happen to the volume of the refrigerant? Increases or decreases? The volume decreases. And what will happen to the pressure? Increases, right? And you know this, I think you're already aware of this. Pressure is directly proportional to temperature or inversely proportional to temperature. Pressure is directly proportional. And you can relate with this concept of temperature. We discussed now, temperature is a function of movement of molecules. As the movement of molecule increases, the pressure, the temperature increases, and the movement of all molecule related to the pressure. So it means as the pressure increases, the temperature also increases. So remember, pressure and temperature are directly proportional. So volume decreases because of compression, and the pressure increases. And as the pressure increases, temperature also increases. Actually, our requirement is to increase the pressure so that we can run the cycle. But since directly this pressure is directly proportional to temperature, the temperature also increases. So how to reduce the temperature? We'll discuss. So you see, the compressed refrigerant in the gas state with the high temperature and pressure, you can see high pressure and high temperature in the vapor come out from the compressor, right? So in order to reduce that pressure, in order to reduce the temperature, first of all, you must change this vapor to the liquid. So what will happen? The refrigerant, which is with a high pressure and temperature, we are supplying to a heat exchanger called condenser. The name will give you the idea. The condenser means condensation will happen inside this, and change of phase from vapor to liquid. So when the refrigerant entering in the condenser in the form of vapor with a high pressure and temperature, so you see it will flow inside this tube, and it's a heat exchanger. So what will happen in the heat exchanger? The heat exchange from this refrigerant to outside, and this exchange of heat can be done with a supply of air. For example, I'm using a fan here, and this fan, when you run the fan, it will suck the air from the outside and is going to throw on this, and you see the outside temperature compared to the refrigerant temperature, it should be less, and it's a high temperature pressure. So assume that the supply air what I'm throwing on that coil is a less temperature. So you know, heat transfer from high to low as per the second law of thermodynamics. So what will happen? This air is responsible to reject the heat off from this refrigerant, which is in the gas form, equal to what? Equal to latent heat, because the vendor, means the manufacturer, will design this condenser, this heat exchanger, to reject the heat equal to the latent heat. And whenever the latent heat, it means when the rejection of latent heat, what will happen to the phase?
Gas to liquid.
Yeah, change of phase. No, latent heat means change of phase. So what will happen? The inlet in the condenser is in high pressure and temperature vapor, and because of the heat rejection to the atmosphere by using the air, so the outlet of this condenser will get again high pressure, high temperature, but in liquid. You see, you know this change of phase means latent heat at what? At constant temperature, na? So temperature is still same, but change of phase in the condenser.
So, one question is
Yes.
this fan is this much of accurate that it can only lower the temperature, or not lower the temperature,
Rejection of heat.
rejection of heat, so that
You see, according based on that only the manufacturer is going to design this, the flow rate of air, the number of coils, the thickness of the coil, dia of coil, then only the system will work. So that is again the component designing. So the manufacturer will design the condenser so that it can able to reject the heat equal to, means not less than equal to the latent heat. Then only the change of phase is possible, right? So that
temperature will be remaining same.
Temperature and pressure both is going to be same, but change of phase, because you know at means latent heat means at constant temperature, na? Okay, so when the refrigerant is coming out from the condenser, it's with the same temperature, pressure, but it changed from what? Vapor to the liquid. Okay, and here one more important point. If you use this fan to cool the condenser, so remember this system, and you can write as a note also. If you want, you can please make a note. This is a very important point. So when you cool the condenser by using a fan, so this system we can call as a air cooled system. And when you cool this condenser by using water, for example, I'm using a separate container, and this complete coil inside the container, and I'm going to supply the water. Suppose here water in, I mean H2O in, and here suppose this H2O out. Means I'm circulating the water on the coil, and the water is responsible to reject the heat of that condenser. So remember, this system will become water cooled condenser. And why I'm explaining this point, because at the time of learning chill water system, means I'm talking about chiller. Chiller is of two types. One is a air cooled chiller and second is a water cooled chiller. And in air cooled and water cooled chiller, only the difference is at condensing site. Rest of the thing is same. So in chapter 5, we'll discuss in detail about the chiller. Don't worry. But I'm just relating because this is important point. So at this level, just remember, if the condenser is cooled by air, we are calling that system. It can be a chill water system. It can be a different system. And all comes under DX. We'll discuss in chapter 5. So the system we can call as air system, air cooled system. If I'm using the water to cool the condenser, that system we can call as a water cooled system. Next. So now you see outlet of the condenser, it is in the refrigerant, it is in the liquid, but still with the same temperature. We are interested to reduce the temperature. So now you see process 3 to 4. So now this refrigerant in the liquid form is allowed to pass through a device called expansion device or expansion valve. It can be a throttling valve or it can be a capillary tube, etc. You'll find the different types in actual practice. But at this level, just focus on the concept. So remember, expansion. With the expansion device, what will happen? Expansion process will take place now. And expansion is a reverse of what?
Compression.
Yes, exactly. So because of expansion inside this, because of expansion process of refrigerant in the liquid form, what will happen to the volume? The volume increases and pressure decreases, and pressure is directly proportional to temperature. So temperature also decreases. Okay. And you see, when the refrigerant is coming out with the low pressure after the expansion process, the pressure is so low, some amount of refrigerant flashes and change to vapor, some amount, by extracting the heat from the remaining liquid refrigerant. And we know that as the pressure decreases, the boiling point of the substance also decreases. So at the outlet of the expansion device, some amount of water, some amount of refrigerant will flash and extract the heat from the remaining liquid refrigerant. Further, it's cooling down, means extracting the heat. And this cool, you see, at the low temperature and pressure refrigerant, when coming out from this expansion device, the outlet of the expansion device is connected to the inlet of one more heat exchanger called evaporator. This is the application site. Okay. So this evaporator, if I use to extract the heat from the food product, this system I can call as a refrigerator. If I use this evaporator to extract the heat from the room air, this I can call as a air conditioner. Or if I use the same to extract the heat from the water, I can call this as a water cooler. I'm not talking about air cooler, that is different. Water cooler, you'll find the water cooler also only to cool the water. You'll get the chill water from that for drinking purpose. So you see, application, we have different application, but the concept is same. So this heat exchanger is called evaporator. So remember, when the low pressure and temperature refrigerant entering in the evaporator, so what will happen? Because of low pressure, the boiling point of that refrigerant also reduces. It means it can start boiling at the low pressure when extracting the heat. So what we'll do, we'll use a fan. For example, I'm taking example of air conditioner. I'm using a fan, and this fan is used to suck the air from the room. And suppose room temperature say 30 degrees centigrade, and this refrigerant temperature say 5 degrees centigrade. For example, or it can consider say 15 degrees. It's depend as per the capacity and other factors. Just for example, so you see 15 degrees temperature is less than 30 now. So when the 30 degree air is going to throw on this coil, and remember, the air is not going to mix with the refrigerant. There is no mass transfer. So this is a copper tubes, and copper is a good exchanger of this is a good conductor. So what will happen? You'll get this temperature of that surface of that copper tubes will drop. Means you'll get the cool copper tubes when the air is thrown on that coil. Okay, on that cooling coil, what will happen? The air heat will extract by the refrigerant. Right? Because again, second law of thermodynamics, heat transfer from high temperature to low temperature. So the refrigerant will extract the heat, and the refrigerant at low pressure means at low boiling point. So it start boiling, and start boiling means it will extract more and more heat. And when the refrigerant is coming out from this evaporator, it will change its phase from liquid to vapor by extracting the heat equal to latent heat. Again, the manufacturer will design this evaporator to extract the heat equal to latent heat. Then only the change of phase from liquid to vapor, means gas, And now at the outlet of this evaporator, the refrigerant condition is what? Low pressure, low temperature, but
Vapor.
in vapor. Again, that low pressure and low temperature vapor, in order to circulate again, we required a system, na? Again, the compressor. So the low pressure and temperature vapor means gas will suck by the compressor, and again the compressor will increase the pressure and temperature. The cycle continues. Okay, so in this way we'll get the cooling effect, and this cooling effect you can utilize for different application. Based on different application, we are dealing with the different, we are calling the different system. Again, further, if you talk about air conditioning, in that also you'll find the different system like DX system or chill water system or air system, etc. We'll discuss in chapter 5. And in actual practice, you'll find here one accumulator, because this accumulator will not allow any refrigerant liquid in compressor. It will bypass back to the circuit. Similarly, you'll find the flash chamber also here. If any gas is in that, it will supply back to this. So in actual practice, you'll find additional components also. Apart from this, you'll find the receiver, because the refrigerant after expansion, it is collected in the receiver, and as per the requirement, it will supply to the evaporator based on the demand. So you'll find a number of components in actual practice. At this level, just focus on the concept, how we are getting the cooling effect. That's it. Yeah. So now if you have any question, we can discuss.
Sir, if I'm summarizing the thing, after expansion valve till the section of compressor, pressure and temperature will be same, right?
Yeah, but you see, outlet of this expansion, it is in
outlet
refrigerant liquid. Outlet of
only the phase change will be occur
yes,
in the
yes.
evaporative coil.
And the same case on the high side also.
Temperature and pressure will be same, but phase change will occur in the condensing coil.
Yes. So
And
just go.
Accumulator is means sorry, receiver is the after the condenser, the
after evaporator. Sorry, oh, my mistake. After condenser.
After condenser.
You'll find this accumulator. Sorry, my mistake. This receiver. Accumulator, this of evaporator, and flash chamber after this condenser. The flash chamber will not allow any gas in the expansion. Accumulator will not allow any liquid in the compressor,
because it's vapor compressor. I think compressor will be damaged.
Yes, because yes, definitely, because compressor is designed to compress the refrigerant in gas state. Okay. Like this, you'll find some more options like controls, etc. in actual cycle. That will I'll show you in chapter 5 at the time of dealing with the Windows split or other systems. Okay. But the important point is, if the condenser is cooled by air, it's an air-cooled system. If the condenser is cooled by water, it's a water-cooled system. Please make a note of this point. We'll use at the time of chill water system also. Apart from this, how the phase change and how this cycle, different process like compression, condensation, and expansion and evaporator. This 4 process, and I've given the point also 1 to 2, 3 to 4, and 4 to 1. The same with reference to that, you'll find the theory in the notes. So this conclude the vapor compression cycle and chapter 3. But you see, related to vapor compression cycle, one more point is pending. That is a condensation on the evaporative coil. And wanted I hold that point, because that point we can discuss only after learning this psychrometric properties, especially the dew point temperature. So let me quickly give you the idea. We talk about the evaporative coil in the previous session. So just remember that when the air is coming out after touching to that evaporative coil, the first point you see, don't get confused, the air and refrigerant will not mix. Refrigerant is within that copper pipe only, means within that evaporator, and he is going to throw on that. Okay, so in actual practice, you'll find the bunch of fins that I'll show you in chapter 5. Don't worry. So when the air is thrown on that evaporative coil, the air loses the heat to the refrigerant. Okay, and remember, in evaporator, the temperature of refrigerant is less or equal to the dew point temperature. So what is exactly dew point temperature? I'll show you in this chapter 4. So whenever the temperature less than equal to dew point temperature, remember the condensation will start. And that's the reason you'll get the water from the AC. How exactly? I'll show you after completing this dew point temperature. Okay, so this dew point temperature again related to vapor compression cycle. We'll discuss. Let me complete this. So in this session, we'll talk about this psychrometry. And this is very, very, very important. Why this is important? Because you see, I think you remember in the first session, we talk about this air conditioning or the HVAC. So in HVAC, what we are doing, we are supposed to maintain the condition of air, either by adding the heat or removing the heat. So what do you think? Without knowing the properties of air, can you think to condition the air? No. So that's the reason we are talking about the psychrometry. So psychrometry is what? Psychrometry is a study of what? Air. In short, we used to call air, but you know this already we discussed. Air means what? Moist air, right? So you see, psychrometry is a study and analysis of property of air and water vapor mixture. Except special cases, in actual practice, you'll find the moist air. Special cases means generally in desert areas or with the low humid areas, you may find the dry air. That is a special case. But when you talk about air means by default, we are considering air and water vapor mixture. And the study of air and water vapor mixture is a psychrometry. Okay. And you must know the properties of air. Then only we can think to condition the air as per the human comfort or as per the process control or as per the application requirement, etc. So it's a very basic topic, but very, very important. Okay, so first we'll talk about the different properties of air. And why we'll talk about the properties of air? So that using psychrometric chart, one can find these properties of air. For what? For the load calculation. Load calculation means again for conditioning the air, because the load calculation is we talk about heating or cooling load calculation. In that we are going to learn how much cooling or heating is required as per the requirement. So without this psychrometric properties, especially when you talk about ventilation, when you talk about infiltration, and when we talk about the CFM, we require the psychrometric analysis. So for all this topic is very, very important and very simple. You can easily understand this. Just you need to just visualize so that you'll get the clear idea about the psychrometry. And after learning the psychrometry, means the properties of air, we'll talk about this psychrometric chart in manual and using the software, so that the same we can use at the time of load calculation to find the properties of air at the time of calculation. Okay. Apart from this, we'll talk about the psychrometric analysis, not in chapter 4 in load calculation, because after learning some more parameters only, we can think for the psychrometric analysis. So in this chapter 4, I'm going to explain the properties of air and the psychrometric chart, manual and software. So let me proceed. So what I explain the same theory here. So there are different types, different properties of air. First, we'll start with the drival temperature. So if you talk about the list, first is the drival temperature. Second is the Weddell temperature. Then we have a dew point temperature. No need to write, everything is there in this note. So first is the drival temperature, second is the Weddell temperature, third is the dew point temperature. Then we have this relative humidity. Then we have humidity ratio. Then we'll talk about enthalpy of air. Okay. So let me start first with the drival temperature. So this is very simple. You see, for example, assume that this is a thermometer at present in my video. Assume that this is not a pen, this is a thermometer. Actually, it's a digital pen, but assume that this is the thermometer and this is the mercury bulb, for example. So with this thermometer, if I measure this room temperature or the outside temperature under shade, not under direct radiation, because remember, when you talk about drival temperature, we are not considering the radiation heat. So under shade, if I measure the outside temperature or if I measure the inside temperature with a normal thermometer, that we used to call drival temperature. Nothing, simple. Or else, for example, if I say today the outside temperature in daytime was 35 degrees centigrade, means I'm talking about drival temperature. Or for example, in this remote, for example, you'll find a button room temperature. When you press that, you see I can find here 28 degrees centigrade, the room temperature. So this temperature is what? Drival temperature. Okay, so the normal temperature or drival temperature both are same. But remember, the important point is here, for calculation point of view, you must remember this, we'll use at the time of calculation, it will measure the sensible heat of air. At the time when we deal with the calculation, like heat gain through wall, glass, partition, etc. For this sensible heat, I believe you already know what is sensible heat. We'll discuss in chapter 3. Na? So to measure the sensible heat, we required this drival temperature. For example, if you want to know how much sensible heat is transferring from outside to inside through wall, we required outside drival temperature and inside drival temperature. That we used to call delta T, outside minus inside. So that is a drival temperature. So the important point, very simple, but the important point, remember, it is used to measure sensible heat of air. That's it. Nothing else. Very simple. So when you watch the news for weather, you'll get the temperature, the maximum temperature and the minimum temperature throughout the day. Na? So they're talking about the drival temperature only. Okay. Next. And we discussed in the first session, the standard temperature for human comfort. As per this ASHRAE standard 55, this indoor environment. So And the table is given for different conditions. So we can consider a standard as 76 degree Fahrenheit. So that is again drivable temperature. Okay. So simple, nothing else, very simple, but we'll use in the at the time of calculation. How to use, I'll show you at the time of load calculation. This level, just focus on this properties of air. Okay. Next, we have this wet bulb temperature. So you see, wet bulb temperature is cannot be explained directly like drivable temperature because this is not the natural property of air. Drivable temperature is a natural property of air, na? But wet bulb is not a direct property of air. This is a property, or this is a temperature will get based on the sling psychrometry, or with the operation of the sling psychrometry. So exactly you cannot understand the concept for this. But anyhow, I have some important points to discuss. So first of all, we'll discuss how to measure this wet bulb temperature, then the purpose, so that you'll get the idea. But remember, this is not like a drivable temperature. Drivable temperature is a direct temperature of air, but wet bulb temperature is not direct temperature of air. It's a temperature taken by a thermometer, which is going to, or with the wet cotton on that bulb, and we are supplying air with a velocity say 3 to 5 meter per second approximately. So what will happen? For example, assume that, just you can watch this in the video. Assume that again this is the thermometer. Assume that this is a thermometer, and assume that this is a wet cotton or a wet cloth. So after measuring the drivable temperature, this is important point. After measuring the drivable temperature, we will do this process. So assume that already I measured the drivable temperature, and the temperature is showing say 27 degrees centigrade in this thermometer, say drivable temperature. Then what I'll do, I'll take a wet cloth or a wet cotton, I'll cover this bulb with the wet cloth. Okay. After that, either I'll rotate this thermometer or else I'll supply air on this bulb approximately 3 to 5 meter per second velocity. So after some time, what will happen? The condition of the cloth, the cotton is what?
Dry condition.
It will dry, na? So how it will dry?
Evaporation of moisture.
Exactly, because you see, when you supply the air, the evaporation process will take place on this wet bulb, na? And you know, evaporation required heat. So at the time of evaporation, what will happen? It will extract the heat from this thermometer bulb. And when it is extracting the heat from the thermometer bulb, what do you think? The temperature is going to be less than 27 degree or more than 27 degree?
Less than.
Less. So 27 degree was drivable temperature. Now, after that, I start the process. Okay, so at the time of this evaporation, the heat will extract from the bulb, resulting in lowering temperature. So that recorded temperature is called wet bulb temperature. Just try to understand the process first, then we'll talk about way to use this. So it's a simple process. Yes.
Just if I'm summarizing the things, same amount of heat is responsible for evaporation as well as sensible heat.
You can consider, you see, in short, you can consider this temperature is this wet bulb temperature is a temperature after evaporation. And again, what you said, this is related to evaporation or evaporative cooling.
Yes.
So let me complete this. Again, we have some more points. So again, I'm going to share the screen. So you see, first of all, get the clear idea about the process. You see, this is called sling psychrometry. In that you'll find this dry bulb and wet bulb. So dry bulb will measure normal thermometer will measure the drivable temperature, and this thermometer with the cotton or a cloth, which is will make it wet. And after that, by this handle, we'll rotate this. Rotating means what will happen? The movement of air. So after some time, the recorded temperature on the below thermometer will find drivable temperature, on the above thermometer will get wet bulb temperature. This is the process. Now the question is why this property is required. Okay, so first of all, as you said, this is related to evaporative cooling. At the time of evaporative cooling, or when you're designing, say, air cooler, this concept can be used. Or else you can take example of evaporative cooling, you know, air cooler works on evaporative cooling. Or else in oil pot, you'll get the cooling based on the evaporative, we will get the cool water based on the evaporative cooling. Na? So these are a few examples for evaporative cooling, but why exactly we require this property? So remember, at the time of dealing with the load calculation, we required the properties of air, like dew point temperature, relative humidity or humidity. Different properties of air is required. So the rule to use a psychrometric chart is you must have minimum 2 properties of air. Then only one can find the other properties of air using psychrometric chart without doing an experiment. Just sitting in office or sitting in home, using psychrometric chart or using psychrometric chart, using psychrometric chart or using psychrometric software, one can find all the properties of air, but the condition is you must have the two properties of air. So dry bulb and wet bulb, two are measurable. No? So dry bulb importance, that is for sensible heat, but wet bulb is not for latent heat. Okay, so that is for evaporation. So then why wet bulb is required? To find the other properties of air using psychrometric chart. Okay, getting your point online?
Can you repeat this point again?
You see, in order to use the psychrometric chart, the condition is if you know two properties of air, then only one can use psychrometric chart or psychrometric software to find other properties of air without any experiment. So dry bulb temperature and wet bulb temperature, both are measurable. No? So if you know this two property, simply using the psychrometric chart or psychrometric software, one can easily find the other properties of air without wasting the time, without doing an experiment, just sitting in office with the chart or software. That's it. And when you use the data book at the time of load calculation, like from ASHRAE or from Carrier, for almost all the cities, except few locations, you'll find the information for dry bulb and wet bulb. Okay, so that is available in the standard handbooks. So we'll use at the time of load calculation. So this is not the direct property of air. This property is based on the experiment. And why we need this property? To find the other properties of air using psychrometric chart. Or for just to understand with more detail, you can consider the temperature at which after condensation. Sorry, my mistake. After evaporation. The temperature at which after evaporation. So how much decrease in temperature? According to that, we can relate with the heat. So that can be used for, say, evaporative cooling. But here in air conditioning, evaporative cooling is different and air conditioning is different. Air cooler is not a part of air conditioner because air cooler will provide only sensible cooling, not the latent cooling. So we'll not discuss more about that evaporative side. So for air conditioning point of view, remember this wet bulb is used to find or to use the psychrometric chart. How to use, that is the next story that I'll show you in chapter 7 at the time of dealing with the load calculation using from this data, ASHRAE data. Okay, next we have dew point temperature. This is also interesting and important. So remember, this dew point temperature is not like a boiling temperature or freezing temperature of water. For example, boiling temperature of water, at atmospheric pressure is 100 degrees centigrade. Freezing temperature, 0 degrees centigrade, atmospheric pressure. Dew point temperature is not similar to that. Dew point temperature will change as per the change in the other properties of air. This is an important point. What exactly dew point temperature I'll explain, don't worry. So this is not like a fixed temperature, like boiling or freezing. This will change as per the other properties of air. Remember this point. But now the question is, what is exactly the dew point temperature? Very simple. You see, dew point temperature is the temperature at which moisture leaves the air and condenses on the object. This is opposite to what? Evaporation. Means, or we can say the temperature at which condensation starts. And again, this is not a fixed temperature like freezing or boiling. The condensation can be happen at different temperature based on the other properties of air. So for that, we require this property to find out from the psychrometric chart. So this may vary as per the dry bulb, wet bulb, and other conditions of air. So once again, dew point temperature is the temperature at which moisture leaves the air and condenses on the object. For example, you see at the beginning of this session, we discussed the air will have the dry air as well as moisture, right? So do you have any proof for that? How this air have the moisture? Because this is not visible to us.
That is dy. Because after in air there is air and moisture in the form of dew. They are condensed
in the form of vapor, right?
Yes.
Which is not visible. Yes. So how we can prove this? Very simple. You know this in day-to-day life. You can relate this. Just consider a glass of water. Just assume that this is a glass of chill water, which I've taken from the refrigerator just now, for example. And the chill water glass, if I place in the room temperature, what will happen after some time at the surface of this glass? The water droplets, you can observe the water droplets now. And this water droplet is not from the water because this is, you see, there is no chance of mass transfer through this glass, right? So this water which is at the surface of the glass is not from that water from the glass. Okay, so this water is going to condense from where? From the room air. Yes, from the room air. So this proved that the air will have the moisture. First point. Now the second point is related to dew point temperature. You see, when you take a chill water in this glass from the refrigerator and place in the room, what will happen at the surface of this glass? what we'll get? We'll get the temperature less than equal to dew point temperature. And remember, whenever a surface or a body, or when you reduce the temperature of the air less than equal to dew point, what will happen? The moisture from the air will leave the moisture from the air will start leaving and condense on that object. So that temperature is nothing but dew point temperature. As the dew forms on the leaves or on the object in winter season, normally in the winter season in the morning time, you can find this dews. So because of what? Because of decrease in temperature, at one point the dew point temperature occur. And again, I'm saying this is not the fixed temperature that you need to find out in the psychrometric chart based on the other properties of air. It's not like a boiling or condensing, is not a boiling or this evaporation temperature or this freezing temperature. This due to dew point temperature will vary as per the condition of air. We'll find out from the psychrometric chart. So simple, the temperature at which the condensation start is called a dew point temperature. Now the question is how it is related to this property, related to this condition of air, how it is related to this HVAC. So we have different aspect for this, but let me just get some important points from the theory. Here one important question for all. What do you think? In which season you'll find higher humidity? Winter or summer? Summer. What about other participant?
Yeah, in summer more humidity will be there.
Right. In winter, less humidity. Why less humidity? So first of all, why summer is wet? More humidity means, can I say wet summer?
No, because the water gets evaporated in the summer.
So we can say wet summer, na? Generally, summers are wet because higher humidity, except desert areas. In general, I'm talking about, not in desert areas. In desert areas, even in summer, you'll not find the wet, means humidity is less because of lack of evaporation of water. In general, summers are wet because of more evaporation. No confusion. No? Now the question is why humidity is less in winter?
Evaporation is less.
Yes, evaporation is less, and further the condensation increases, right? And
dew point temperature is less. No?
Right. So generally dew point temperature you'll find in winter, na? And whenever the dew point temperature or less than dew point temperature, what will happen? The air, the moisture from the air start leaving from the air and condense on the object. So there is a reason winters are dry and summers are wet. And because of this, winters are dry, we required heating and what? Humidification. We'll discuss this point in chapter 7. Don't worry, just I'm giving the preview. And in summer, we required cooling and dehumidification. Okay. And humidification means increasing the moisture. Dehumidification means extracting the moisture. Okay, so remember this process we'll use at the time of load calculation. Again, this is related to dew point temperature. Apart from this dew point temperature is important for the vapor compression cycle also. So now one more point here. In summer, we required what? Cool and dry air or cool and moist air?
Cool and dry air.
Cool and dry air, na? Because we required cooling and dehumidification. So this cool and dry air you can expect through this evaporative coil. I'm talking about vapor compression cycle. Now assume that this vapor compression cycle I'm using in what? Window AC. I think everyone can relate the window AC, na? If you don't know, don't worry, we have this in chapter 5. So in window AC, you'll find all the components of vapor compression cycle, what we discuss. Okay. So when you get the air through the window AC or a split AC, you'll get the cool and dry air. How exactly? We'll discuss now. So let me open this chapter. Back to this vapor compression cycle. I believe you already have the old notes, no? So in that you can find out chapter 3 and you can add this point, or else you can write somewhere. Later you can update in this when I share. So here in vapor compression cycle, I believe it's visible on screen. So you know this, we are using a fan which will supply the air from the room, right? Suppose room air is 30 degrees centigrade and room air is what? Hot and humid. So when the room air is flowing on this coil, what will happen? You will get cool and dry air. This is important. And cool air means you can understand because of exchange of heat. Extraction of this room air heat by this refrigerant. We already learned this process. And why this dry air? So remember, the refrigerant temperature is so low, the temperature is less than dew point temperature. And you know this, whenever temperature less than equal to dew point temperature, condensation start, na? So refrigerant temperature is low temperature and low pressure. So the temperature is less than, remember, in refrigerator or in air conditioning, we can expect the latent cooling. And latent cooling means the temperature should be less than the dew point temperature. In air cooler, you'll not get the latent cooling, you'll get only sensible cooling. So latent cooling means the temperature less than the dew point temperature or equal to less than dew point temperature. It means that when the refrigerant is flowing, the temperature of refrigerant is less than equal to dew point temperature. So when the refrigerant is flowing inside this coil and air is thrown on the coil, the surface of this the surface temperature is less than dew point temperature of that air. Yes,
one minute, sir. The less than or equals to temperature of the water. I mean, that means moisture.
Yes.
Not the
refrigerant, because the water from the air is going to condense, na? Okay. So, and the manufacturer will design in such a way, and definitely you see you may find nearly say 15 degrees or less than that temperature. So you can expect this dew point temperature. Anyhow, how to find dew point temperature, I'll show you today only in the psychrometric chart. What will happen? The moisture in the air is going to condense on the coil. You see, condense on the coil, not in the coil. So the water droplet is going to form on the coil, and there is going to be drain at the bottom. If it is a window AC, you will get the water from the window AC. Did you notice that one? Or else in split AC, indoor unit will find the water. Na? So that water from where? That is from the room air only. There is a condensed water on the evaporative coil. Because of what? Because of dew point temperature. So remember, this vapor chromatography cycle means air conditioning system will provide the cool and dry air as per the requirement. In summer, we don't require separate dehumidification process. In case of process control, where we require low humidities, in that case we require separate dehumidifier. But for home and comfort, this cycle itself will provide you the cool and dry air. Okay. In case if you talk about data center means server rooms, we required low humidity because the machine don't require the humidity. In that you'll find the special system. In that you'll find the name of the system like crack unit on the particular model. So in that you can low humidity levels, means it will extract maximum moisture from the air. Okay, it may maintain say 10 to 20% or less than that. But for home and comfort, we require what? 30 to 60. Na? Okay, so that can easily done by this evaporative coil. And we have a standard 1 ton will extract. If you want, you can make a note of this. We'll discuss at the time of chapter 5 also. 1 ton will extract 1.2 liters per hour. This is standard. It may vary as per the cooling capacity and as per the efficiency, but standard for interview point of view is the extraction or the dehumidification rate of dehumidification is for 1 ton is 1.2 liters in 1 hour. We'll discuss more about this at the time of chapter 5. Back to the topic. So I think you got the idea about the dew point temperature.
Is it depend upon the load on the evaporator? Means 1.2 liter per hour.
That is a stand. You see, 1.2 is just a standard, like a thumb rule, like 1 TR equal to 400 CFM, no? Similar to that. But this may vary because you see, extraction of moisture depend on the condition of room also, no? If the room air moisture is less, so how it will extract? So in some cases, when you switch on the air conditioning in summer, after some time you'll feel dryness because extraction is more and the moisture is less in the air. So that's the reason fresh air is also required. Okay, that is a different process. We'll not mix it at this level. So at this level, just standard. There is not a fix that will vary as per the different conditions that you need to find out. Yes.
One question. We have to maintain 30 to 60% of relative humidity. So if all the dry air touches the evaporative coil, I mean all the vapor will be condensed. I mean in a dew form. I mean it will be very dry. Then how to maintain this 30 to 60%?
You see, the first point is the evaporative coil is not designed to extract the complete moisture. The first point. Okay. Second point, continuously we are providing the fresh air. Okay. And you see, I'm not talking about window or split. Window and split is not a standard units because that there is no option for fresh air except some options, but not a standard one. So I'm not talking about the window and split. But if we talk about in the standard air conditioning, right from this ductable split or the central type, in that we are providing the fresh air also. And fresh air means continuously is providing the outside air means that with the moisture. Okay, again that also depend as per the outside condition. In some areas you'll find lower humidity, so the process will change. In that case, we require cooling and humidification. But what we are discussing is just general. So I think got the clear idea about this dew point temperature, which is important.
So next, how the humidification process is completed? I mean, we need to sprinkle the water. How humidification process?
Humidification. Okay, you see what we discussed just now is a dehumidification. Yeah. Humidification means adding the moisture. Adding the moisture in with the heating. So we may add the steam in the duct.
Okay.
or you'll find the separate humidifier. Simple, it's a simple process. The humidifier can be add the heat by steam by this with a normal heater, or we can provide with separate steamer that adding the moisture means in the duct or in the room. And for that we have a separate hygrometer to measure this. Anyhow, that is the other story. Don't mix at this level. Just at this level, just try to focus what is dry dew point temperature. That's it. We'll discuss more about the systems process next. So I think got the idea about the dew point temperature online. Next we have relative humidity. Very, very important. And you know the importance of relative humidity, because in the starting sessions only we discussed now for human comfort, the two major parameters. First is the temperature, second is a RH. Right. So before dealing with the relative humidity, I believe you already know what is humidity. Just now we discussed now, the moisture present in the air is a humidity, or the moisture content is a humidity. Then what is relative humidity? The name will give you some idea. Relative means it's relating with something. So better to discuss first humidity ratio, then relative humidity. First, let me explain humidity ratio. Then we'll talk about this relative humidity. So it's simple. Humidity ratio is what? Also known as specific humidity. Specific means per unit volume, no? Per unit if you measure, that we can call as a specific. So humidity ratio or specific humidity, both are same. It's a fundamental property in psychrometry that represent the mass of water vapor present in a unit mass of dry air. For example, if I take 1 kg of air, and in that if I got say 200 grams of moisture, so 1 kg I'm just measuring for 1 kg, na? 1 kg unit, okay, means unit volume. In that if I got say 200 grams of moisture, so that I can call as a humidity ratio. And if you want to get the total humidity, we'll multiply with the total volume. So in case of English system, we are measuring kg per kg of dry air. This kg is a air and this kg is a moisture. Similarly, in case of English system, we are measuring grains per pound of dry air. If you want, you can measure in pounds per pound of dry air. First pound is a air, second pound is a moisture. You see, this is, or else you can use the term grams per kg, not grains. Grains is different. Grams, I'm talking about grams. The unit can be grams per kg of dry air. So 1 kg dry air, in that say 200 grams. So the unit can be grams per kg of dry air, or the unit can be kg per kg of dry air. This kg is a moisture and the second kg is a air. This is in English, this is in metric system. Similarly, in English system, one can use pound per pound of dry air. First pound is for moisture, second pound is for air. Or else we can use this grains per pound of dry air. So 1 grain, remember, sorry, 1 pound equal to 7,000 grains. This is again unit of English system. So don't get confused. This is not gram, this is grains. So grains per pound of dry air instead of pounds per pound of dry air to avoid confusion. So most commonly in English system, we are using this unit, grains per pound of dry air instead of pound per pound of dry air. In metric system, we are using grams per kg of dry air, or strictly SI, kg per kg. So simply humidity ratio is what? Moisture present in the air for a unit volume, nothing but the humidity. And if you want to know the total humidity, we'll multiply with the total volume at the time of calculation. And remember, this humidity ratio will use at the time of latent heat calculation. Sensible heat will use, drivable temperature will use for sensible heat calculation. Similarly, this humidity ratio to find out, to deal with the latent heat, because if you know the quantity, then only we can find out the latent heat. How exactly? I'll show you in the load calculation. Don't worry. At this level, just try to understand these properties. Now we'll discuss very, very important property, humidity ratio. Sorry, my mistake. Relative humidity. This is important for interview point of view also. So relative humidity means what? Relating with the saturated condition of air. I'll give an example. Assume that in this classroom, day one, this is the classroom. So day one, I'm measuring the temperature. Suppose I'm maintaining the temperature is 76 degree Fahrenheit. And by using a humidifier, I'm continuously adding the moisture. Suppose with the humidifier, I'm continuously adding the moisture. And after say 1 hour, when I measure the humidity inside this, I got say 10 pounds. You see, degree Fahrenheit, so I'm using pound to avoid confusion. I'm using this system. So, and again after 2 hours, when I measure, I got 10 pounds. Even after 5 hours also, when I measure, I got 10 pounds. It means the maximum moisture possible at this temperature in this room is what? You see, at 76 degree Fahrenheit, 10 pound of moisture is what? You saw line?
Maximum.
Right. Maximum. The maximum possible moisture content at this temperature in this room is 10 pounds. It means RH is 100%. And I can use one more term. The air is saturated. Remember, when the RH 100%, it means we can say the saturated air. Means the air contained the maximum possible moisture content at that drivable temperature. And remember, we cannot change the temperature. We need to measure at that particular drivable temperature, because as the temperature increases, the holding capacity of moisture by the air increases. And as the temperature decreases, the holding capacity of moisture by the air will decreases. Again, this is related to evaporation and condensation. So at this temperature, in this room, the maximum possible moisture content is 10 pound. It means RH is 100%. This was day 1. Now day 2. Now in day 2, just I measure this. I'm maintaining this same temperature, 76 degree Fahrenheit, and I'm not adding any moisture. Just I measure, and I got say 5 pounds. So it means RH I can consider as what? 50%. On what basis I can consider this RH as 50%?
Base is the saturation condition.
Yes, because we know that at this temperature, you see, you cannot measure with a different temperature. At the same table temperature, when you compare the present moisture with the moisture when the air gets saturated, that comparison is nothing but relative humidity. Matlab, what can be the maximum possible and what is the present, that comparison is nothing but relative humidity. And remember, whatever the temperature you're maintaining for human comfort, at this temperature, if you maintain 30 to 60% moisture level, it means you're maintaining comfort. What we all discussed at the starting session, for human comfort, the humidity level should be 30 to 60 na? And below 30, what will happen? Dryness of skin. And above 30, sweat, and the stickiness, the muddy condition. So in both the condition, that is not comfort. So that's the reason the range is 30 to 60. So whatever the maximum possible moisture at that particular temperature, if you maintain 30 to 60, it means you can maintain the comfort with respect to moisture for human. So that's the reason this relative humidity is important. Got it online?
Sir, any relation in between the relative humidity and the humidity ratio?
Humidity ratio is the quantity of the moisture. That is a measure of the moisture. But relative humidity is a comparison of the moisture. Both are humidity only. But one is the actual quantity of that moisture that we can measure per pound. If you measure per pound, you can multiply with the total volume. You'll get the total moisture in the room. That is calculated irrespective of the temperature. But this RH is related to a particular temperature. What can be the maximum and what is the present? That comparison is nothing but RH.
I mean, for example, 76 degree Fahrenheit, we have 10 lV moisture. That 10 lV moisture is humidity ratio, right? The amount.
Yes, you can consider humidity. This 10 pound you can consider as a humidity, total humidity, not humidity ratio, because humidity ratio is a specific.
I mean, unit volume.
This you can call as a total humidity. Total humidity or total moisture present in the room. But if you measure for 1 pound, then you can say humidity ratio or a specific humidity. So both are interrelated. It's not different. But relative humidity means we are comparing with what? Saturated, with the saturated condition at the same temperature. This is an important point. Do not compare with a different temperature, because different temperature means the holding capacity of moisture will vary. At the same temperature, if you measure or if you compare the moisture level, that comparison is nothing but humidity, relative humidity. Okay.
And this relative humidity is most important when we do the heat load calculation, right?
Yes, for comfort. Actually, this is for comfort. This is one of the parameter for human comfort. So for example, if I'm feeling comfort at 72 degree Fahrenheit, because you see this temperature also will vary as per application and as per human to human. Exactly, we don't have exact temperature for all human being, because we discuss some people will feel comfort at 72, some will feel at 76, some will feel at 68. You see, if a person eating more calorie food, the heat released from the body is high, so he will not feel comfort at 76. He will feel comfort at 68 degree Fahrenheit. Okay, so that also depends. So for example, if I'm feeling at comfort at 70 degree Fahrenheit, for that particular condition, the humidity level should be 30 to 60% in between, so that either I'll not feel the dryness of skin or I'll not feel the sweat, means thickness of the skin, thickness means this muddiness. And you see one more point, if the humidity level above 60 degree, it will affect to the breathing also. I have just given some important points. Let me complete this. Sorry, muggy condition, sweaty and sticky, and you see irritated to respiratory system also. Even if the humidity level above that condition, about the 60%, it will affect to even the breathing also. And you can relate this. You see, generally in summer, when you get the rain, sometime in summer also you'll get some rain. Immediately after rain, you'll feel difficulty in breathing, because in summer temperature is high, and because of rain, water also available. So water evaporates and the humidity level extend to maximum. And because of that, we cannot breathe easy. That is one just you can relate. Yes, online?
No, sir, I can relate that design is not too much easy thing. It's a very critical thing.
Talk about precision air conditioning or process control, yes. But for human comfort, we already have the standards. You see, we are in the modern world, so most of the thing is available as a standard. So you must learn how to use that in a proper way. So you are not doing, will not do the research, will not extract the codes and standard. We already have. So we'll learn how to use that in a proper way as per the requirement. That's the reason concept learning is important. And that is also reason why I'm focusing more on the starting topics, because all this will use at the time of load calculation. See what I explained the same. Relative humidity, amount of moisture that a given amount of air is holding by the amount of moisture that is given the amount the air can hold. Okay, means at the saturation condition. And remember, when the air is saturated, one more point, if you want, you can make a note of this. When the air is in saturated condition, dry bulb, wet bulb, and dew point temperature will be same. I'll show you in the psychrometric chart. At the 100% RH line, the three properties value is going to be same. I'll show you next only. This may ask in interview. So when the air in saturated condition means when the RH is 100%, dry bulb, comma, wet bulb, and dew point temperature value will be same. Quickly, I'll show you. We'll learn how to use the psychrometric chart, but quickly, let me show you this point. I'll show you how to use the psychrometric chart, but at this level, you see this point. This line is 100% RH line. This one, this curve. And this 70 is wet bulb temperature. Below 70 is a dry bulb temperature. And dew point temperature you will find here. So now, for example, if I put the point here, you see this is at RH 100%, na? This point. So you see this dew point temperature is 70 degree Fahrenheit. Dry bulb temperature is 70 degree Fahrenheit. On the right side, dew point temperature also 70 degree Fahrenheit. This is one important point to consider for interview point of view. But how to use this psychrometric chart, we'll discuss now after completing the enthalpy. The next humidity ratio already we discussed. Now this note we'll discuss. Let me complete the enthalpy first. So I think, remember, we already discussed about enthalpy. What is enthalpy? In short, heat content.
Total heat content of the system.
Right, heat content of the system or a substance. Then why we are talking about enthalpy again? You see, this time we are talking about enthalpy for air. And the important point is, remember, the enthalpy of air, for air also it's a heat content. But for what? For dry air and the moisture. That's it. You see, enthalpy will consider for, let me mark the important point, related to the latent heat, total heat content of the air. That includes sensible plus latent. So enthalpy is heat only, but for air, since we discuss the air is what, the psychrometry is what property of dry air and moist air. No? So remember, enthalpy of air is a summation of sensible and the latent. Sensible refers to the dry air and the latent refers to this moisture. Okay, so that will be the total enthalpy of air. And at the time of calculation, we'll talk about the total enthalpy, not just enthalpy of dry air or the moisture. This is one important point. Rest of the thing, you know what is enthalpy. Next, now we'll talk about this psychrometric chart. Now, before that, this note, as I said, as I've given at the beginning, you see, for the psychrometric chart, if you have information about any 2 out of the 5 air properties. So if you know the dry bulb, wet bulb, or dry bulb RH, or any 2 properties, you can calculate the remaining 3 properties using psychrometric chart. This is a condition to use a psychrometric chart. So now, in order to use the psychrometric chart, you must know what line represent what property. Okay, so for that I have given this information here. You see, first, dry bulb temperature. Can you see the highlighted lines? 1 minute, let me pause this. The first one. You see the vertical lines on psychrometric chart represent what? Dry bulb temperature. See, it will show in the vertical line, but increase in horizontal direction. To show you the vertical lines, but increase in a horizontal direction. For example, you see this 40, 50, 60. So increase in horizontal, but represent with the vertical lines. This is first property, simple. Second is what?
Dew point temperature. Sorry, wet
You
bulb
see
temperature.
wet bulb. So wet bulb temperature, you can find out this inclined lines. You can see the highlighted line. The inclined line represent the wet bulb. But don't get confused. Inclined line is for wet bulb as well as for enthalpy. But you'll find the two different scales. You see? Can you see this enthalpy also highlighted with the inclined lines with the same inclination? Can you see this online? The enthalpy, right side. Inclined line, this inclined line, this inclination and this inclination for wet bulb are same. But you'll find the two different scales. Okay, but the same line orientation. So don't get confused. Dry bulb represent with the vertical lines, wet bulb and enthalpy with the inclined lines towards left with the two different scales. I'll show you on the psychrometric chart, don't worry. Next, dew point temperature. You see here, dew point temperature, horizontal line share with the humidity ratio. You can see left side is the dew point temperature. You can see the highlighting of this horizontal line. On the right side, humidity ratio. That is also horizontal line, but with the two different scales. You'll find the two separate scale, but both represent or orientation with the horizontal only. Similarly, RH with the separate curved lines. Simple, very simple. So if you know what line represent what property, with the two known properties, one can find all other properties of air using the psychrometric chart. Okay, so we'll do one simple example using this psychrometric chart. This is taken from train. In this way, you can find the point. I'll show you. This is just example. Now we'll verify this example first. You see in this example, what are the two known properties given? 95-degree Fahrenheit dry bulb is given and 78-degree Fahrenheit wet bulb is given. Okay, so dry bulb with the vertical lines, na? You see, this is dry bulb and wet bulb is what? Inclined line. This is 17. And if you just intersect, you'll get the point. This is a point. Once you get the point, if you go in the right direction, this is what?
Dew point temperature.
Dew point temperature. And on the same horizontal with a different scale, you will find humidity ratio also. I'll show you. And apart from this, you see this inclined line is 40 and this close to this point, this RH line is showing 50. Na? So RH we can say 50%. This is one example. We'll do one example in the class. Don't worry. This is just a preview. So here we'll do an example. Example one, you see, assume that this classroom at present, the classroom temperature, what I've measured at the beginning is 28 I got in the remote. Just assume that 27 degrees centigrade, this room temperature at present where I'm sitting. And for example, RH is 60%. So you see, I have not measured RH 60%. On what basis I can consider 60%? Based on my feelings. You can measure with a hygrometer. We have a separate tool for that to measure this RH, but I don't have right now. So 60%, I'm just assuming based on the condition, because in this room now, I'm not feeling the dryness of skin. Either I'm not feeling the sweat. You see in my skin, there is no sweat and I'm not feeling the dryness of skin. So that's the reason I'm considering 60%. For example, you'll find one more example below. So now 27 degrees centigrade and 60% RH. And the chart what I'm using on screen, this is, see, this is based on English system. You see 70, 80, this is English system. No? You can find the metric system. I'll share you the software. Already I shared the software. Under SMT software, you can find out the psychrometric software. But this is a manual chart, psychrometric chart at present taken from train, and this is English system. And here quickly conversion is required. So 27 degrees centigrade, if you convert into Fahrenheit, you know the conversion already discussed. Na? F equal to 1.8 C plus 32. So I got 80 point something round off to 81 degree Fahrenheit. So now I have two properties. One is the dry bulb, second is the RH. So let me use the psychrometric chart just carefully on screen. Very simple. So we have two properties now. You see 81 is a dry bulb. So can you read this 80 here? And this is 90. So this is 95. So 95 means each division is 1 unit. Na? So this I can consider as 81, right? And RH 60%. So you see this is 10%, 20%, 30, 40, 50, 60. So this is 60% RH line. So if I go straight up and intersect with the RH line, you need to use the scale. At present roughly I'm using. You see this is the point, right? This is 60% line, 60% RH, and 81 what dry bulb. So this is a point. Now with this point, if I go incline parallel to this what wet bulb line, I can find the wet bulb temperature. No? So wet bulb is what? 71 point. You see 75 now, this is 71. In between I'm getting. So 70.5 degree Fahrenheit. Exactly you can measure with the scale. Now roughly I'm taking. This is WBT. Now, if I go beyond this and if I mark here, you'll get enthalpy. Enthalpy and the wet bulb temperature with the same inclination with the different scale as I said. Na? You see, you'll find the different scale. And this enthalpy is what? Dry air and the moisture. The total enthalpy, not just dry air. So now this is 30 what? BTU. You see the unit is BTU per pound of the dry air and the moisture. Or I can say BTU per pound. Pound means the total enthalpy. So this is 30, 35. So 31, 32, 33, 34, right? So H is what? 34.5, no? 1, 2, 3, 4, right? At this level, if you want, you can add up also. Now with this point, if I go straight on the right side with the horizontal orientation, it is somewhat difficult. Yes, I got this. And if I, so you see, first of all, what humidity ratio? Humidity ratio we can represent with the omega or W is what? 90, 100. Can I consider roughly 95? 95 what? Grains per pound of dry air. Remember this unit. You can find somewhere. You see, grains of moisture per pound of dry air. In some psychrometric chart, you'll find pound per pound of moisture. Pound per pound of the dry air. Don't get confused. You need to verify the units. Mostly we are using this grains per pound of dry air. Next, dew point temperature 60. I can roughly take can take 66, right? This is what? DPT. Can I take 66 degree Fahrenheit? Right, simple. So if you know any two properties of air, we can get the point. With the point, if you go in the respective direction orientation, you can find out the other properties of air. For what? For load calculation. In the time of load calculation, we required these properties of air to find out this heat gain through ventilation or infiltration. For delta W means humidity. This delta refers to the humidity ratio. So difference in humidity ratio required. This property is required. So we can find out with other two properties of the room air or the outside air. We required, for example, delta W means we required WO minus WI. WO is the outside humidity ratio. WI is the inside humidity ratio. So in order to find out this WI and WO and WI, so WO we can find out with the outside two conditions like dry bulb and wet bulb. WI we can find out with the inside two conditions like dry bulb and RH. RH we are maintaining 50%. So one can find delta W that can be used to find out the latent heat gain through ventilation and infiltration. This is example, but don't worry, we'll do the calculation at the time of load calculation. Okay.
Also, I'm not getting this point. Can you explain?
Which one?
The delta W.
Delta W is what? Difference of outside humidity ratio minus inside humidity ratio. So in order to find out this WO, we require two outside condition. And two outside conditions say dry bulb and wet bulb. If you know this, using psychrometric chart, we can find out this WO. Na? Similarly, for WI, we required say dry bulb and RH. RH, we are maintaining 50% standard. Dry bulb is a 76. Using these two parameters, we can find out WI. Once you know this, we can find delta W, which is required to find out the latent heat gain through ventilation and infiltration. This is just example. We'll do the calculation. Don't worry. At the time of load calculation, when we deal with the ventilation and infiltration, we'll find out this delta W. This is just a preview. At this level, just focus on how to use the psychrometric chart. That's it.
Delta W is difference of humidity ratio, right?
Between outside to inside. Forget about this. This is just I have given the preview. But this is important at this level. If you know this, then we can calculate this at the time of load calculation. We'll do at the load calculation. This is just a preview. This side is important. How to use the psychrometric chart. That is important. Clear online? So some more examples are given in the notes, even in your previous notes also. You can try this example after the class. You'll find some more points related to psychrometry, like humidification, dehumidification, contact factor, bypass factor, and this coil, you see the black color is a coil curves. We'll discuss this. At this level, I'm not explaining this because at this level, we are just learning how to use this psychrometric chart. At the time of application, we'll discuss more points like contact, bypass factor. That is very, very important. Now, how to use this psychrometric software, which is further easy. So you can find out the psychrometric software under the SMT software folder and just double click and install. After completing the installation, you can find out the psychrometric software. You see how to use, very simple. First, you must select the type of the chart. And you see what we did till now, this manual chart. Remember, this is based on atmospheric pressure, or in other words, I can say the standard psychrometric chart is based on the atmospheric pressure. Barometric pressure 29.9 inches of mercury, or else 760. If you convert into mm, you'll get 760 mm of Hg, or 1 bar. So this is atmospheric pressure, na? So the standard psychrometric chart is based on the atmospheric pressure. If your project location is above or below the altitude, means sea level, we can change this. You see, we have this 2,500 feet above sea level, 5,000 feet above sea level, 7,500 feet above sea level. Okay. So as per the location, we can change, but mostly we are using this standard at sea level. And when I click the sea level, you can find the same. You see 29.92 inches of Hg, or else if I change this to metric, you see I can change simply metric by clicking this SI, means SI metric. You can notice, you see 101.325 kilopascal, nothing but one bar, na? Or 760 mm of Hg. You know these conversions. So you can decide which unit you want to use. According to that, you can select. For example, again, I'm using IP because the example what we did in manual is IP. After that, what you do, simply verify this psychrometric chart number. Suppose I'm using carrier 1. Then use this option, state, point, and process. When you click this, you'll get a window. In that window, click add a point and provide the 2 parameters. The example 1 was 81 degree Fahrenheit dry bulb. You see, dry bulb is a basic requirement. And after that, the second property you can select. So second property in that example, we consider RH. Na? I'm selecting RH and enter 60, for example. When you enter this, you'll get all the properties. You can read. You see wet bulb is 70.5, what we got. RH is what we have given. W is what? Humidity ratios 90. Here you see what we got, 95. 1 minute. We got nearly that. I think I have written wrong, but you see this unit is important. You must verify. In some charts, you'll find pounds per pound. Here it is given grains per pound, which will match with the previous manual chart. So don't get confused. Here you'll find specific volume, some more parameter. Enthalpy 34.5 we have taken, we got 34.4. Dew point temperature 65.5 we have taken, 65.8. You can add up to 66. You can find all this property. And when you click apply, close, you can notice the point you can find here. New one. I have not renamed, that's the reason I got new one. So you can rename also. You see, I'm going to name this as, say, room condition. You'll get the point here. And we'll get all the properties. Very simple. No need to verify from the chart directly. You can click here, you'll get all this parameter. And further, we have psychrometric calculator also from ASHRAE, which is same like this table. Let me show you. You see this psychrometric calculator, which I already share in the under this SMT softwares. Here in this table, if you enter the known properties, the 2 known is what? Dry bulb, say 81, and RH we have 60 in the example 1. In example 2 is different. You can find the properties. And in this, you see, you can select grains per pound of dryer or pound per pound of dryer for the units given. Or else if you refer this example number 2, you see dry bulb is 60, wet bulb is 55. So dry bulb I am entering 60, wet bulb say 55. Now I can verify all the points. You see, R is 74. Here I'm getting 73.2. Just this was taken from the chart, so it's a rough. And humidity ratio 56. Here I got 56. Here 56.59, so I can round off to 57. Dew point temperature 51. Here 51.4, so I can take 50. And enthalpy 24. Enthalpy 23.19. So this is from the chart. This is more accurate. In actual practice, at the time of load calculation, we'll use the psychrometric chart or the psychrometric software. In manual also you can use, because that much accuracy we don't require, because we are not dealing with with the component designing. No? We are dealing with the system design. If you're dealing with the precision air conditioning, then more accuracy required. But for home and comfort, either you can use the one chart also. Okay, so this was about chapter 3. Simple, limited, but very important. But some more points like psychrometric analysis, contact factor, bypass factor, humidification, dehumidification, heating process, cooling process, all this we'll discuss. This is not actually the end of psychrometry.